Okay, so today we're going to start Chapter 5, and we're going to begin with 5.1, Estimating with Finite Sums. Let's talk about distance traveled first. Consider the following problem. So a train moves along a track at a steady rate of 75 miles per hour, and that's from 7 a.m. to 9 a.m. What is the total distance traveled by the train? So you may remember all the way back Algebra 1, distance equals rate times time. So we identify what part is the rate. Well, that's the 75 miles per hour. And then the time, so if we're talking from 7 a.m. to 9 a.m., that's 2 equals 2 hours. So the distance equals, so we have 75 miles per hour. Now keep in mind that's miles per hour, so that when I multiply it by 2 hours, right, our units of time will cancel, so we are left with 150 miles. So that's the distance traveled. Again, the key here, this is a steady rate, a constant rate. So let's make a connection between this formula and the graph of the velocity function. So what we're going to work with in this chapter, and we've worked with previously, what if the x-axis is now the time axis and the velocity is where your y-axis? So take into consideration v of t in this case is 75. And one of the things we had said is it's a steady rate, it's a constant rate. So we have this velocity function equal to 75. Now we don't know when the train started and stopped, we just know that from 7 a.m. to 9 a.m. We looked at the rate of, we looked at the distance that was traveled. So remember, this is 2 hours. And if I take a look here, the height of this is 75. So we can actually relate this function to the area of the triangle. So we're looking at the area under the curve, the area under that straight line, and the area would be base times height. So we have 2 times 75, so we get 150. Again, that would represent 150 miles. So again, what did we notice? We noticed that the distance traveled is exactly the area of the rectangle. So why is that important? Well, first of all, trains, cars, airplanes, lots of real applications, they don't stay at a constant rate. They have a velocity that varies. So what happens if the train's velocity varies as a function of time? So the graph would no longer be the rectangle. In fact, our velocity might go something like this. Now, the question I pose here is, would the area of this irregular region, so again, let's identify here's 7 a.m. and here's 9 a.m. So we look at this region, this irregular region. Would that still give the total distance traveled over the time? So if we found out this area, would that still represent the total distance traveled? And our answer is yes. So this area represents the total distance traveled. Now, unfortunately, with an irregular shape like this, we don't have an area formula that we can just use to establish, the base times the height. Now, as I just said, we can use base times height, but we don't have just one rectangle. So what we're going to do is we're going to partition. Okay, so Newton and Leibniz, they decided, okay, what if we partition it, which means break it up into tiny subintervals, so that each one is so small that the velocity over it would essentially be constant. So in other words, we're trying to make little tiny strips of rectangles. So geometrically, this was equivalent to slicing the irregular region into narrow strips. So basically, take this same function from 7 to 9, and we're going to divide it into tiny strips. Okay, so we imagine many, many strips, and we can basically approximate it. Now, eventually we're going to look at the exact area, and that's going to be using what we call an integral, and that's going to be using a limit. But for right now, in this lesson and in the next lesson, what we're going to do is we are going to do approximations. Because right now, all we know are the straightforward area formulas. We can find the area of a circle, we can find the area of a triangle, we can find the area of a trapezoid. And so what we're going to do for this lesson is we're going to break our shapes up into rectangular strips, because we know the area of a rectangle is base times height. Now, what would be the base? Well, the base, okay, picture these tiny subintervals. The base is basically the length on the x-axis. On the x-axis, or I'll write here the t-axis. Whereas the height is going to be determined by the function. Okay, so whatever function we might have, if we have the velocity function, that's going to be the height. So like, for example, when we did the one that was constant, the height ended up being just 75. Okay, whereas here, we're going to have irregular, so we might have to actually figure out what that height is at different time intervals. Okay. And then we're basically going to add, so we're going to sum all the areas to find that total distance. Okay, so we have 3 different methods we're going to learn about today, because there's 3 different ways that we could create these rectangles. So these are called rectangular approximation method. Okay, again, the width of each rectangle, or like I said, the base, is basically the length of each subinterval. And then the height is basically the function's value at each endpoint. So we have 3 different methods. We have LRAM, which is the left-hand rectangular approximation method. This uses left endpoints of each interval to determine the height. RRAM, which is the right-hand rectangular approximation method. This uses right endpoints of each interval to determine the height. And then we have MRAM, the midpoint rectangular approximation method. So that uses the midpoint of each interval to determine the height. Okay, so example 1, we want to estimate the area under the curve. So we're not doing an actual application problem just yet, but we want to look at, here's a function. Our function is f of x equals x squared. It could be any function, it's just, this is the example that I gave you. And we want to approximate the area under the curve from 0 to 3. And there are 6 subintervals. So first we're going to do left hand, then we'll do right hand, and then we'll do midpoint approximation. Okay, so first thing we want to do is kind of look at each of our subintervals. So if it goes from 0 to 3, each subinterval, or the base of our rectangle, the way we can, an easy way to determine that if it's equal intervals, we just take the interval 3 minus 0, or a length of 3, divided by 6. So each base of our rectangle is going to be a half. So it's going to go from 0 to a half, then a half to 1, then 1 half to 3 halves, 3 halves to 2, 2 to 5 halves, and then we have 3. Okay, so for LRAM, what we want to look at is each interval. Okay, so each interval, so our first interval goes from 0 to a half. So we have the base of that rectangle is a half, and then the height, it's kind of confusing on the first one because the left endpoint actually is 0. So we plug in 0 into our function, so it's going to be 0 squared. Plus, next we're going to go to the next subinterval. So that's going to go from 1/2 to 1. Again, the length of that base is still 1/2. But this time the height, well, we're going to plug in 1/2 because we want to figure out what the height of that rectangle is. And that's going to be 1/2 squared. Plus, next, we want to go from 1/2 to 3/2. Again, we want to determine the height by the left endpoint. Next, we'll do the right endpoint, which means we would have used the 3/2. But here, we have 1/2, and the height is determined by 1 squared. Next, we have from 3/2 to 2. The base is 1/2, and the height we get by plugging in 3/2 squared. Next one, again, the base is 1/2, and then the height is determined by the left endpoint, which happens to be 2. And finally, our last one, still base is 1/2, and this time the left endpoint is determined by 5/2, so that's 5/2 squared. Now, you may recognize when they're equally partitioned, I could have just pulled the 1/2 out in front, but if there's 6 subintervals, I should have 6 rectangles added together. I should have the sum of 6 parts added. And, I would recommend go ahead and plug this into your calculator and just verify that you do get 6.875. Now, we can easily see with this left-hand approximation that the rectangles are all under the curve. So we're going to talk about later what does that mean if they're under the curve, and you'll see in your homework. You can see that this is an underestimate. So so the actual curve, the area under the curve, is going to be bigger than this approximation that we have here. And then when we look at the right-hand rectangular approximation method, if you notice all our rectangles this time, they're all over the curve. So there's going to be an overestimation. Now let's go through the process again. This time, just to save some time, I'm going to multiply 1/2 to the front, and then we're just going to multiply all the heights. So again, all these subintervals have the same numbers here, but we're not going to go from our first rectangle doesn't use 0 as the height. It uses 1/2 because we're using the right-hand endpoint. So that's going to be 1/2 squared. Next rectangle, we use the right-hand endpoint, so we're plugging in 1 squared. Next one, we plug in 3/2. We want the right-hand endpoint. Next one, we go up. There's 2 squared. Next one goes to 5/2. Again, it's completely the opposite of what we just did. So instead of using the left-hand endpoints, we're using the right-hand endpoints. So we go to 5/2 squared, and then here, go to 3 and 3 squared. Add all those up, and we get 11.375. So again, if the left-hand approximation was 6.875 and our right-hand approximation was 11.375, you know the actual area under the curve is going to be somewhere in between. Now midpoint, this one's going to be a little more complicated just because we're not using any one of the endpoints. We're using the midpoints of the endpoints. So if we look above from 0 to 1/2, we're going to use 1/4 to determine the height of that first rectangle. Here, we're going to use 3/4 to determine the rectangle's height. Here, we're going to use 5/4, then 7/4, then 9/4, then 11/4. So for midpoint, again, the base for each of these is still 1/2 in length. It's only the heights that change. So now we're going to plug in 1/4 squared. Again, the reason we're squaring it is because we're doing f of x equals x squared. If it was a different function, we'd plug 1/4 into something different. So plus 3/4 squared plus 5/4 squared plus 7/4 squared plus 9/4 squared plus 11/4 squared. Again, we should still have the sum of 1, 2, 3, 4, 5, 6 parts. And here we get about 8.9375. And that's actually going to be a little bit more precise. Now the reason we have these three different methods, and especially on the AP exam, they're going to tell you which approximation method to use. So if they want you to use RRAM, they're going to specify. Okay, and there are some times where we have to use one and not the other. I gave you the function in this case, but sometimes I don't give you the function. Sometimes we'll just give you a table of values, so we don't know what the actual curve is going to be, which is what we're going to look at in the next case. So we have this table below. It shows the velocity of a model train. So the velocity is inches per second, and it's going along this track for 10 seconds. We want to estimate the distance traveled by the engine using 10 intervals of length 1, and that would be 1 second. And if you notice, they increase by 1 second, 0, 1, 2, 3, 4, 5. They don't always get evenly distributed this way, and that's where things get a little more complicated. For these, however, we want to estimate the distance traveled using LRAM, and then we'll do RRAM. So for part A, now because all of the base, okay, so basically the base is 1 for each of these, right? The base is 1. So I'm going to do the base, which is 1, and then I'm going to multiply that by all the heights. Now the height, if you want to think about this as you could plot these points like on an actual graph. So at 0 I'd have 1, 2, 3, 4, and then at 1 I'd have up to 12. Right up here, let's say that's 12, and I can make these different rectangles. So for example, the first one would be a rectangle that would be 1 by 4. In other words, we just use that velocity. The velocity is our height. So the first rectangle is going to have a height of 4. The second rectangle is going to go up here to 12, and then so on. So basically we're going to use all of these except for the last one, which happens to be 0. If you recall, you may have noticed when we did these, the LRAM and the RRAM back here, I stopped here. When I did LRAM, I stopped at 5/2, and I didn't use the 3 because the 3 happened to be a right-hand endpoint. Versus here with RRAM, I did use the 3, right? But I didn't use the 0, which was a left-hand endpoint. So it's a very similar approach when we have a table of values. And for these, we simply just add them together. The computation involved is not very difficult. So for this one, we should get 87. Or actually, hold on 1 second, I think it's 91. Go ahead and add that up, double check my work. So we have 4 plus 12 plus 22 plus 10 plus 5 plus 13 plus 11 plus 6 plus 2 plus 6. Yeah, 91. So that represents how far it traveled, and since we were talking time was in seconds and this was inches per second, so it went 91 inches. Now for B, for RRAM, I'm not going to use the 4. I'm going to start with 12. And I'm going to add these numbers all together. And then I do include the 0 at the end, although that's not really going to have any impact on it. And we get 87 inches. Okay. Example 3, a particle starts at x equals 0 and moves along the x-axis with a velocity v of t equals 6 for t greater than or equal to 0. Where is the particle at t equals 6? So this is kind of like the very first type of problems that I was referring to. You know, here's your time axis, here's your v of t. So if it's going 6, and that's constant, and it's starting at 0 and it ends at 6, so we're thinking, what's the area of that triangle? It's 36, And since it starts out at x equals 0, that's something we'll discuss later on. Sometimes the particle doesn't start at a position of 0. Sometimes it starts out at a different position. But for these, we're just going to multiply. So I have distance traveled. So basically my distance is going to be 6 times 6 is 36. And I don't have any units here, so I'm just going to leave that. Okay. A particle starts at x equals 0 and moves along the x-axis with velocity v of t equals negative 2t plus 6 for t greater than or equal to 0. Where is the particle at t equals 3? So this one is going to be a little bit more involved just because notice the velocity this time is not constant. It's the equation of a line, right? Just think y equals negative 2x plus 6. So I'm going to graph that line. And it's going to go like this. So here's v of t, which was negative 2t plus 6, and here is 3. And this is my time axis, velocity. So it doesn't happen to be a rectangle this time, but it does end up being a triangle. So we think about, can we find the area of that triangle? Sure. So my distance this time is going to be basically 1/2. The base is 3. The height is 6, so we get 9. So the total distance traveled here by this particle is equal to 9. Example number 5. A car comes to a stop 10 seconds after the driver applies the brakes. While the brakes are on, the velocities of the car are listed below. Use midpoint approximations with 5 subintervals of equal length to estimate the distance the car traveled while the driver was braking. Okay, so since this is over 10 seconds and we want 5 subintervals of equal length, that means each subinterval is going to be equal to 2 seconds. So from 0 to 2, from 2 to 4, 4 to 6, 6 to 8, and 8 to 10. Those are my subintervals. So basically with midpoint, okay, so my subinterval is 2 seconds, so that's equal to the base of my rectangle. So it's going to be 2 times. Well, what's the 2 times? Well, I'm using subintervals. So if I'm looking from 0 to 2, the midpoint would be at 1 second. So the velocity here, these are my heights. So basically I have 76 plus, then my next subinterval is from 2 to 4. So I want the midpoint, which is at going 57 feet per second. Plus, then the next subinterval is from 4 to 6. I want to use 42. The next subinterval is from 6 to 8. So my height is 29. Next one is from 8 to 10, so I have 3. Again, I should have, since I have 5 subintervals, I should have 5 numbers added together. Again, this is really base times height plus base times height plus base times height. It's just that the base was all equal to 2, which is why I didn't have to keep writing that. So I'm going to multiply, let me add all these, 76 plus 57 plus 42 plus 29 plus 3 gives us 207. So we're going to multiply that by 2 and we get 414, and we needed units. So we had, this was in seconds, feet per second. So it went about 414 feet after the car started braking. Okay, example number 6. The table below records the velocity of a car in miles per hour at different time intervals over 25 seconds. Use LRAM to approximate the total distance traveled. Note the differences in units. So what that means is, first of all, this is in seconds. This is in miles per hour. So we actually have a choice. We could change the seconds to hours. We can change the miles per hour to miles per second. Or we can just convert everything at the end. So I just want to keep in mind, if we're using seconds and miles per hour, there are 3,600 seconds in 1 hour. I'm going to convert it at the end. I think that's a little bit easier, so we'll do that. Okay, so for LRAM, now the complicated thing here is these are different time intervals. Notice we no longer have equivalent time intervals. So the first one, our base of our rectangle, is actually equal to 4. So I have 4, and since this is LRAM, I want to use 0, the first one. Next one is from 4 to 6, so my base is 2, times a height of 20. Next base is 3. 6 to 9 is 3 seconds. Now we use 31. Next one, from 9 to 10, we have base is 1 second times 47. Next one, 10 to 14, is a difference of 4 seconds times 50. 14 to 17, the base is 3. Height is 52. Base from 17 to 20 is 3 times 54. 20 to 21, base is 1. Height is 60. And from 21 to 25, the base is 4. And the height is 56. So I should have used all the values except for the 55. Now if this was RRAM, we would have skipped the 0 and we would have gone and started with 20 and ended with 55. Okay, so now we want to add this all together. So 4 times 0, that's 0. We have 2 times 20 plus 3 times 31 plus 1 times 47 plus 4 times 50 plus 3 times 52 plus 3 times 54 plus 1 times 60 plus 4 times 56. Now we get 982. Now remember, we have to go back here, and this doesn't represent feet, doesn't represent miles. What we have to do is we have to convert it. So if we take through 982 and we divide by 3600, we get about 0.2727. This is actually miles, so I'm okay with writing in miles. Or if you want to multiply that by 5,280 feet, so if I multiply that, we get 1,440.27 feet. If I don't specify, either answer is correct. It's just a matter of which one do you prefer.